Assalamu alaikum everyone. So we had now laid the foundations to Perceptron Learning Algorithm. We know how it learns, and we also said that we have to prove its convergence, proof of convergence. And we mathematically model the proof of convergence. Okay, the first thing is we have to make sure that the data is linearly separable. The assumption in that was data is linearly separable. Why am I showing you this proof? Again, for the sake of proving, that's the first thing. And the thing is that I want to show you how to prove things. If you have to sometimes prove things and you will be given a physical example, a real world example, first you will have to computationally model it, you will have to bring it into mathematics, and once you are convinced, okay, this is the thing that I have to prove, and then you should know how to prove things. Okay, we have it in between in probability also. I showed you certain proofs, so here again we'll go with this. So the first assumption that we'll take here, that this data is linearly separable, and after this, so I'll now state this formally. So now you have two finite sets of data, finite sets, so which we call it P and N. So P is for positive points, N is for negative points. Okay, and they are in n-dimensional space, okay, which we wrote previously also. So they are in n-dimensional space, and then we have to show that Perceptron Learning Algorithm, it converges. That we have to show that there is a W star. W star is that optimal W. It is that normal vector to the plane. So when we take this positive point, so if we take W transpose of this star, this should be greater than equal to 0 for positive points, and for negative points, W star transpose dot X, that is dot product of this, should be less than 0. So this is what I mean by convergence. So it should not make any mistakes. Okay, as I said, the first definition that I write, what is linear separability? So that is, this is also called as linearly separable. So if this thing happens, if there is the W star, that is for all the positive points, this will happen, and for all the negative points, this will happen. So this is the definition of linearly separable data. Okay, so what we can do is, now in order to prove this thing, so what I have to prove is, if I make the update, so as I said previously, if you just see the geometrical interpretation, so you have this W, okay, and this is the, let's suppose, plane that this W belongs to, and now you have this point which is misclassified. So that means this angle over here, the angle it is making with this is less than 90. So it should have been greater than 90. So you have to make it such that it should be greater than 90 then. Okay. So you have to something to do with this. So you have this W, let's call this T. Okay, WT means the current WT, and WT plus 1 is the updated one once we update this. So you somehow have to show that within limited number of steps, it should converge, the WT plus 1. So once we take this WT to WT plus 1, we should be sure that in limited number of steps, it somehow makes the it does the data separation in such a way that this is followed, that for all these positive points, it is greater than 0 when we perform the dot product, and for all the negative points, it's less than 0. Okay, now we'll see it how. So what we can do is, like, for the simplicity, we can transform this negative points into positive points. So how can we do that? So if we have this negative point N, so if we have a point which belongs to this, let's suppose X. So if I write X belongs to N, so let's suppose if I take minus N, that will belong to positive class then. So it is like just having a reflection. So I'll make it like this. So you have this plane. So let's suppose these were the positive points and these were the negative points. See, this was a negative point and this was a negative point. If I take minus X, probably it will be here and here. So I'm just flipping this. I'm taking the converse of this. That means if it was initially in the negative class, now it will be in the positive class. Am I clear till this point? So this is one thing that I want you to be sure of. That is, I am making an assumption. I am converting this negative points into positive points. So why am I doing it? So that I have a set of points. Let's suppose I will have a set of points now P. Any point I can take it from either positive class or union of negative class. So now all these points will be my positive points. I think we have a question. Yes, please go ahead. So I'll just answer the question over here. The question was, let's suppose this is the coordinate system. I'll just clarify it if somebody has this question. So whenever I say something about W, that means this W is the normal vector to the plane. So let's call this as plane. So we have this 2D coordinate system. So this is our 2D coordinate system. So now points can be anywhere. You can have point here, you can have here, you can have here. Let's suppose you can have points here, anywhere in this. So now when I am drawing this line, suppose I am drawing this line, say this is a plane which is separating them quite perfectly and it's having error of 0. So I am drawing the W. This W is the normal vector to this plane, or in this case to the line. when I'm updating this W. So let's suppose I update this W towards this. So what is happening basically is I am basically updating the plane. Okay, so this is the updated plane, this is the initial plane. Okay, and this is determined by W's. So you have W initial and you have W final, something of this sort. Okay, I hope this clarifies some of the doubts. The first thing which I said is we have made an assumption. So if initially we had a point which belonged to negative class, so what I'm saying is I'll have minus x. Now it will belong to positive class. So now I'll have all the points P which will belong to either positive or negative of this. So all of these will be positive points. Okay, I hope this assumption is clear. So this is what we're making. Why are we making this assumption? Because if I now take any P, if I take any P from this class, so if I take a W, if I initially randomly initialize W and I take W transpose of that x, it will be always greater than or equal to 0. So this is what I have to do, because now all the points are positive and this is what it should satisfy. So once I am transforming this into positive points, so any W, if it rightly classifies all those points, then if I take any point, this P, let's call this P now. So if I take any of the P, that P is from positive class or negative one, that's also positive class, then it should follow this. So it should rightly classify, it should give me this as greater than or equal to 0. That's dot product of W and P should be this. Okay. Now we'll do one more thing. So one more thing that can be done is we'll normalize the vector. So if you have this P point, so we have P which will belong to, let's call this now P dash, say this is P dash. So P dash here is P union N dash and minus rather. So you have this P which is P dash. So if we take any P from this P dash now, okay, we'll normalize the vector because we are now concerned in the direction. So what is the meaning of normalization? So this mod of P should be equal to 1, that's magnitude should be 1. So we'll normalize it. How can we normalize? If you have any vector P, let's suppose, divide it by its magnitude. So if you have P1 say, divide it by magnitude of P1, so you'll get this as a normal vector. So you'll normalize it. So this is what, because it will simplify our analysis. So these are the things. The first thing which I said is you have to do this. So this is the first thing and this is the second thing, we're normalizing. Okay. The second thing is we now want to find the optimal W. The assumption is that the data is linearly separable. If the data is linearly separable, that means there must be W star. This is given, there must be the W star. So for this W star, if we take all of these P, all of which belongs to this P dash, because now we know how the P dash is defined. So for all of this, if I take W star, I'll write it like this, W star transpose dot P, that is dot product of this with P, this should be greater than or equal to 0. Okay, this is what should be given to me. That should exist this. Okay, this is the third condition. Because the assumption is, because I am using the assumption here, assumption is that this data is linearly separable. So by using assumption, there must be a W star which should somehow linearly separate the data, and we should be dividing the data into class 1 and class 2. Okay. Now what was the perceptron learning algorithm? The perceptron learning algorithm will initially randomly initialize this W naught. We'll call this W naught. Okay. So the step 1 in the, if you remember that, so step 1 in that was randomly initialize W naught. So this is randomly initialize. Randomly initialize this, and what we'll do is we'll repeat it until convergence. Okay, so till it's not converged, so we'll repeat something. We're repeating a step, repeat until convergence, and you know what's the meaning of convergence. We have also seen the code of this. So repeat until, what should we repeat? So we'll pick up a point randomly. So we'll pick a P belongs to P dash. We'll pick a P randomly. So if, so then we'll write condition if W of this, let's suppose if we have Wi at a particular time instance, or a Wt, let's suppose, if Wt of this transfer, if dot product is less than 0, that means the point is wrongly classified, it's misclassified, then we'll update this. So we'll say Wt plus 1 is equal to Wt plus P. Okay, how many of you remember this? So this is how we update the rule, and then otherwise do nothing. So here else do nothing. Okay, and then come out of this. Okay, then here we'll check for the convergence. It's all the points. So wherever, when you go through, when you cycle with all the points and you do not have the, if this condition is never satisfied, if no point is misclassified, then you will say that we have converged. The data, our algorithm has converged, because it has now clearly classified positive class points into positive class and negative class points into negative class. How many of you understood this? Okay, again repeating this. So why are we doing this? Why are we converting this negative class into positive class? So that we have to do proof for only one case. Otherwise, we have to separately do it for positive points and negative points. So in order to save us from that, at least one more trouble of doing it separately, so we'll just convert. We could have done other way around also. We could have done convert positive points to negative points, and we'll have to do this. So here in the rather than this condition, we'll say greater than 0, and then we'll update it. Okay. So this is what we'll do now. We will prove this now. The proof that we have to show is that this perceptron will take finite time step. So this updation will happen finite times. It will not go infinitely. Okay, if we have to find this W star, it will not keep on going on. Okay, it will some way, there will be a point where we'll stop, because it will have classified the data clearly if the data is linearly separate. Okay, so let's suppose, when do we update? Now we have to see when do we update. Okay, we update on this condition. When we misclassify, that is where we update it. Okay, so if this is the case, if W transpose dot P, so if you take any point, let's suppose at P ith case, so if this is less than or equal to 0, that means we have to make a correction. We have to make a correction. So why should you make a correction? Because this is misclassification. This over here is misclassification. Okay, now we'll update it. Once we update it, so it will go to, we have, let's suppose WT, it should go to WT plus 1. So how are these two quantities related? WT plus 1 is equal to WT plus P. We're adding the P to that, okay, because it is misclassified. Now if you see what is happening with the B, what is happening with that angle. So if I write the dot product, so I can write WT multiplied by WT plus 1. These two vectors. So initially the vector was this, WT was like this. So I have to update it. Let's suppose WT plus 1 was like this now. So I have this angle is there. Let's call this maybe alpha, beta, whatever. Let's call this angle beta or theta, whatever you call it. Say beta. Okay, this angle. Now if I take dot product of this, if I say dot product of WT plus WT plus 1, if I take dot product, so what is that equal to? That is equal to magnitude of this, cos theta or cos beta in this case. Magnitude of WT, magnitude of WT plus 1, cos of beta. So this is how, if I, oops, give me a second. Something happened. Okay. Okay, till here it's clear. If I take dot product of these things, so I should be going till here. So now what I can do is, I can do like this. I can say cos of beta. So this cos of beta, it is equal to, so now let's suppose I have to find this optimal W. By definition, I have to find optimal W. Say I have this optimal W, W star is there. Okay, W star multiplied by W T plus 1. So if I keep on updating, let's suppose I update it a lot of times, and I have to see what will happen with this angle. Say I have this W star, and there will be some angle, it will form with this is the dot product, and divided by mod of WT plus 1, okay, multiplied by mod of this. So I'll have normalized this. So mod of, if you take mod of W star, so that will be equal to 1, because I have normalized this. So I need not to write this. So okay, this is the case right now. So once I reach this W star, so once I reach this W star, so I'll have some angle that will be formed between this. Now I have to see, okay, how many times do I have to do updation? If the updation is for the infinite times, then I am stuck. I am not proving the convergence. Somehow I should prove that this beta is somehow confined. So we'll reach beta in some finite steps. Okay, or we'll just take some finite step. This is bounded somehow. So we'll have to prove the boundedness. Okay, so this once we keep on updating, this updation is happening within a finite number of steps, and we'll say that we have converged if this is not going to infinity. Okay, now we'll see a detailed treatment of this numerator and denominator. So if you take this W star dot product with WT plus 1, so this is what we have. Okay, W star WT plus 1. So now if I take this numerator, so how can I expand it? Okay, I'll show you how to expand this. So this can be written like this. So this is W star dot product. WT plus 1 is basically previous T plus P. Okay, this is WT plus P. Everybody agreeing with me on this? So because I'm just expanding this. Okay, this is the dot product, and I can expand it more. This is equal to W star dot W plus W star P plus W star. This is W star WT. Okay, I think this is the case. So I multiplied this with this. I just opened the brackets up. Okay, W star dot WT plus W star dot P. This is what I did. Everybody with me so far? Now I'll just do one more thing. So now I have these PIs. I have P1, P2, which all of these belong to till Pn. All of these belong to that P dash. Okay. So if I multiply this with W star, if I multiply them with W star, as all of these are positive points, so all of these will be greater than 0. This will be all greater than 0. This will be greater than 0, greater than 0. All of them. But there will be some least point. Let's suppose this is say 1.1. Say this is 0.9. Say this is 0.3. All of these are positive. So there will be one least point. Let me call that delta. Okay, so what is this delta? So this delta is defined that among all of these, so there will be least. So this delta basically is less than equal to W star Pi. Take any Pi. So this W and multiply it with the W star. Multiply with the optimal W, because we know that there should be optimal W. So this delta is basically less than equal to this, because this is the least number that we got from any of these. So okay, how many of you understood this step? Okay, if you understand this delta, now I can expand it. So this is equal to, so this is W transpose, this is W star. I should keep on writing transpose, but that's all right. So here this is being got dot product, and now I can just, this is the point which I can take any other point. I can replace it with delta. Okay, now this will not be equal to, this thing will be equal to greater than equal to. Okay, so you should understand this point. So now W star Wt plus 1 is greater than equal to W star Wt plus delta. Why? Because this is the least point. So if I take any random point, that will be either equal to or greater than. That's why I have written greater than equal to this. Everybody should agree on this point with me. Okay, if you understood the definition of delta, so this is what I came to. And now I can expand this Wt also. So I can say this is greater than equal to W star. So this Wt can be written as Wt minus 1, T minus 1 plus P. Because if I had made the correction, I would have added plus P to it also. And this is plus W plus delta. And I can expand it more. So I'll say W star Wt minus 1 plus W star some other P. Okay, plus delta. And this again can be replaced by delta. This will be some other delta, but it will still be some. I can combine this delta. I can say is greater than equal to W star dot Wt plus 1 plus 2 delta. Okay, if I keep on going this till W naught. Okay, recursively, if I keep on doing, if I keep on substituting the values, so this is T minus 1. If I keep on doing it recursively, so you will see this will be W star dot W0. Okay, plus how many times delta? So I am doing it t times. So I am running the algorithm t times until convergence. So I should say, let's suppose there is some number, because updation is not made for every step. Updation is made for only the things which are misclassified. So if there is a misclassification, that will make updation. Otherwise, we will not make the updation. So in total, we are assuming that the algorithm runs t times. T is the maximum number of steps it runs. T can be, let's suppose if we want to see, it can be infinite as well. But here updation will happen only limited number of times. So let's call that updation, say some step m times. This is running m times. Okay, how many of you understood this m? So here m is less than or equal to t. So it can either, for all the points it will be updated. Sometimes it will be updated for less number of points. That's why I'm saying this m is less than equal to t. T is the number of basically number of iterations we are doing. If we are doing infinite iterations, we are doing it infinite times. So, but it will be either for all the iterations for all the points. Let's suppose. So these this thing basically can be updated if everything is misclassified, or if some of them are correctly classified, then this will be less than t. Okay, as I said, the assumption here is that t should be finite, so we should do it for finite points. So this t cannot go to infinity, because the first assumption was we have finite p union u. So this is what we are doing. So how many of you understood this constant m over here? Okay, again going through. So what we are up to now, so we are saying this cos beta is equal W star dot Wt plus 1 divided by this. So I did the treatment to the to this numerator. What I came up with, I said this numerator should be greater than W star dot W naught plus m times W. So initially we started with this, and we will finally reach this W star. Okay, and with this m times delta will happen. Now I'll do the treatment of this Wt plus 1. Okay, so let's do that. So what I can do is I can write Wt plus 1 square like this. So I can say this is Wt plus p, okay, and multiplied by Wt plus p 2 times. Okay, so I am just doing the treatment to the square of this term. Okay, this is square, and I am opening this up. So if I now open this, so this will be magnitude of Wt, okay, square plus 2 times W times t transpose multiplied by p plus, so transpose is everything because I am writing the dot product, p square. Okay, this is I expanded this. Okay, this multiplied by this multiplied by this multiplied by this, and then p square. So if you see this, so this is equal to Wt square plus 2 times Wt transpose of p, and this is equal to 1, because this is under normal, because we have normalized all of these p's. If we keep on going, now what we'll do is we'll keep on doing this. So now we'll take this, let's suppose we'll go to t minus 1, and we'll keep on doing this. So if we keep on doing this, what will happen is, okay, so what will happen over here is, so if you even see this quantity, let's suppose I'll do one more thing. So if you take this quantity, we'll see one more quantity, we can reduce it. So we know that if we take dot product of this t, because it was misclassified, so this thing is less than 0. Okay, so I can write this thing over here is less than W transpose whole square plus 1. Okay, less than or equal to, because this can be either 0 or less than 0. Okay, so it should be strictly less than 0. How many of you understood this point? Because this was misclassified point. So if you take dot product of these two, Okay, so this will be some negative quantity. Okay, so this was a quantity which had some negative quantity. If I remove the negative quantity, so this quantity will become more. Okay, that's why I'm saying this quantity over here, that means this W transpose plus 1. So this will be less than this W transpose square plus 1. How many of you agree on this point? Now if you see this, so I have to do this for Wt minus 1 now. Okay, if I keep on doing this, so this will be less than if I expand this also. So now what will happen is it will keep on happening. So till once I go to W naught, okay, so I'll have m times of this one. So I'll have plus m or plus m. This m is again less than equal to 2t, because once I expand this, so you will somehow get this and plus one more term plus 1. So I'll keep on adding those ones. So this 1 will be m times 1. So that will be m. Okay, I'll be left with this. So now I have two things. So I have Wt plus 1 square, this, or I can write it like this. This is less than under root of W naught square plus m. Okay, so if I cancel, I should not cancel like this. Okay, so if you see this, so I got this so far. Okay, so if I got this, now if you see this angle, the other thing that I got is the numerator. So now what I can write is cos beta. If I put the cos beta's value, so cos beta, let me see it if I have written so that I don't. Okay, now the cos beta, that is equal to W star W naught plus k times delta. Okay, and I should not even write equal to. This is the numerator. So if you see it over here, okay, this term over here, so W star Wt plus this, and this is greater than this, so this, and then in the numerator divided by, in the numerator I should write this. So this is under root of W naught square plus k. Okay, so if this term is greater than and this term is less than, okay, cos beta, now you see this cos beta, so you have, initially it was equal to, so now numerator, this was actually greater than and this was less than, so this will be greater than this. How many of you understood this? So this point over here, so because the numerator was now greater than and this was less than, okay, so that means the whole term will be greater than this cos beta should be greater than this. Okay, cos beta should be rather equal to also, because the upper side was equal. Now you see this is there are two terms, so this is somehow proportional to this k and this k. Okay, if you take this, that I have written k in here, so here in my case it should be m. Okay, in my case it should be m over here, because I am taking m times, and clearly m is less than equal to t. T is the number of steps. So what I am saying is the numerator was greater. Okay, this was greater than that the numerator that we originally had. Okay, and this was less than, so in whole this should be greater than equal, so this symbol should be greater, and you should convince yourself of this, because the initial numerator that we have, we changed that and we got that numerator is we got this equation, and then we got this less than. So that from those two things what I am concluding is cos beta is greater or equal to this thing. Okay, now if you see this, now cos beta grows somehow towards this. So if you here we have a root of k and we have this, so cos beta somehow grows proportional to under root of m. Okay, there is some relation with this. So if you see this proportionality, because both numerator as well as denominator, so it goes proportionally to this root of m, because we have m divided by root m. If you rationalize it, you will get this root of m. So what I am saying is this cos beta is proportional to this root of m. Now if this root of m is infinity, so this cos beta should accordingly grow with this, but you know that cos is bounded. Cos is bounded by 1, so the maximum value of cos that you have can be 1. Okay, once you have this one, that means this cannot go to infinity. So this thing cannot go to infinity, because cos beta, the value of cos beta cannot go to infinity. So if you take this to infinity, so we will assume that this will go to, so that this means this thing is bounded. So this root of m, this will be bounded, because cos beta has the maximum value of cos beta is equal to 1. So as we increase this cos of beta, so if we make it arbitrarily large, that means if we make it any large, still you have to bound cos beta by 1, because the maximum value the cos beta can take is 1. That means this will not be infinitely long. So here there must be some maximum value where cos beta becomes 1. Okay, so it will be bound by that. So now we are saying if this does not grow infinity, that means this will be bounded. So m is bounded, m is not infinity. That means m will be something finite. So if m is finite, that means as we assume that there should be the w star, so we will find that w star in finite number of steps. So how many of you people understand this? The first question was why this delta? So why this delta over here? So if you understand definition of delta, we have all the positive points. So under the assumption that the data is linearly separable, that means that if I take the dot product of any of these points with this w star, that will be a positive quantity, that will be greater than or equal to 0. Okay, it will be non-negative. So now what I am doing is I am taking least among them. So if I take any least, that is delta. So why am I taking the least? Because I want to establish this relationship. I want to establish this w star dot wt plus 1. It should be greater than this. Okay, that's why I'm taking this delta. That's the rationale behind delta. The second point is why I'm writing it like this now. Now what I said is if a is equal to b, and let's say a is equal to b divided by say some d. I'm saying b is greater than some x and d is less than some y. Okay, so if I just take this, so I can clearly write it as a is greater than this, no, and b was greater than x, so I can write a is then greater than this x. Okay, and then similarly for this, so this case holds. So that's why I wrote cos of beta is greater than or equal to this. Okay, when it is greater, so I got this m term in both of these. I got in denominator and numerator. So from this, what I can say is cos beta grows proportional to this root of m. But I know that I cannot go till infinity in cos beta because cos beta is bounded by this. Okay, that's why I have to take finite step. This was the proof. And second thing was why this angle? What are we adding? So if we have w transpose of, let's suppose, some wt dot x, if it is less than 0, and if this x was a positive point. Okay, now we know this is misclassified. What I said is, I said you should see wt plus 1 is equal wt plus x. So you should add this x. So why should you do it? The proof goes like this. If you take the angle initially, so if you take angle between this, so you initially had this angle. Suppose your point was this. This was your positive point. Now if you see the angle between this positive, this was greater than 90. Okay, my point is, my job is to get it less than 90. I should get angle less than 90. I should make it somehow lesser than 90. So if I have this, so if I write w, let's suppose transpose dot wt plus 1. Okay, if I see this, I know by cross product, if I write it like this, so now I'll say cos of, if I compute cos of theta for this, and if I compute cos of theta of initially, let's suppose this is the optimal w star is the optimal w, cos of theta for this, and if I say w star dot wt plus 1, if I compute theta for both of these things, so let's suppose call this theta t and call this theta t plus 1, you can easily compute that angle by using the definition of dot product, and that will see cos theta. So by this, if you add x, so if you add x, if basically you do wt plus 1 is equal to wt plus x. If you do this, so from this relation you will see that this theta t plus 1 will be less than, or if you want to it should be less than theta t. So this should be the relation that we should have. So that, given the condition that we add this plus x, then only you will get this. So what I'm trying to do is, I'm trying to update this w. This was initial w, wt. So I want to update this w such a way so that this angle becomes less, because it was larger than 90, it should be less than 90. It was initially greater than 90. I want this. That's why I'm adding this x. So what will this x2, on adding this x, we will make sure that this wt plus 1 is less than wt, because this was, let's suppose, greater than 90. That's why we are misclassifying. Okay, and sometimes this also will be greater than 90 still. Then we have to do multiple steps in order to get it, and that's why in either step, but we want to ensure that this theta t is getting decreased. So this is for the positive points, and similarly for negative points, when I subtract that x, so what will happen is that t plus 1 and t will have this relation. So you are making the angle greater than. So angle between the normal vector and you are making it greater. It might not happen in one step. It might happen in multiple steps. But this is the thing that we want to respect. And each time, in case of misclassification with positive points, the angle should get somewhat less. And in case of negative points, the angle should somewhat get more. This is what, and this will happen only in this case if you add x, and this will happen if you subtract x. Okay. So these are the two questions we addressed. And again, I'll go through the algorithm. The first thing that we did is, so the first thing was we converted all the negative points to the positive points. Okay, and then we normalized this p, because there is nothing wrong in doing this, because we just wanted its magnitude to be 1. Okay, once we did that, so algorithm somehow changed. Now we don't have to do 2 steps. We have to just do 1 step, because every point is now considered to be positive point. So now if we take the dot product of the point and the vector, so if it is less than 0, that means it's a misclassification. At that point, we'll have to add this p, add this x that I gave the explanation of. Okay, so now we'll have to see that this classification, when you do this update, it will happen finite. Only happen finite times, not happen infinitely. So we said cos beta is this. If we have this optimal w, because the assumption is this optimal w will be there, because data is linearly separable. And then we'll update this wt plus 1, and this is the relation between this. I'll take this numerator and the denominator. I expand the numerator. This is what I got. Okay, by expanding the numerator, I got this w transpose w star dot w naught plus m times the delta, and this is greater than this. And when I expand the numerator, what I got this wt plus 1 is under root of w naught square plus m. So what I said is, I said this w cos of beta is then greater than this. So if it is greater, you see the proportionality. If it is proportional, as beta is bound, that means this should not go till infinity. This should be some finite. Okay, I hope the proof is clear now. And if you saw, we proved a convergence of PLA, that is Perceptron Learning Algorithm. So now what we'll be doing is, so we will now see what is the actual application, because we have been seeing a lot of binary modeling. By binary modeling, I mean that we model all the gates like AND gate, OR gate, that all was based on binary. So we'll have to see first the applications. So is it actually used somewhere? Is this binary thing will it actually be used? So first thing, if you see, we will take a real world example. So imagine that you are building a system to predict, say, if a customer will buy your product or not. Okay, so that this is what you are, let's suppose, building. Okay, so in that, the first we'll have to see data. So we'll have to do data collection. So I'll be giving this example because this example will serve as a running example everywhere. So whatever we'll be doing today, maybe tomorrow, so we'll take this example. So in that data, we'll have a lot of features. So we'll have features x1, x2, x3 till xn. So say I'll just name a few. The first x1 feature is time spent on the product page. Okay, so time spent on product page. Similarly, let's call this x1. Similarly, x2 can be a number of related products viewed. So number of related products viewed. And similarly, x3 average customer average purchase history. Okay, so we can also write this average history. By that I mean in dollars. Okay, and all of the features will be there. So we can somehow make these features as binary as well. So let's suppose if time spent is greater than 10 minutes, so you call it 1, otherwise 0. So we'll sort of binarize these features, if that is a word. So we can binarize. Okay, and then this also, if number of product related, if it is greater than, let's suppose, 3, then we can have 1, otherwise 0. Okay, greater than 3 is 1. Similarly, average history, our average amount spent throughout the history, if this is above certain dollars, so we can convert the whole problem into a binary problem. So after that, what we can do is, now you have this data. Okay, you have x1, x2, and so on till xn. And similarly, now you have y1. Not this is just call it y. So y basically is, should we sell the product? Okay, will customer purchase the product? So will customer purchase the product? So as I said already, so now we can make all of these features binary. So you will have customer one. Say this is customer one. So it will have some 100 something, something of this sort. And maybe let's suppose customer will have purchased this product, and we'll have data like this. Similarly, we'll have for customer two, data will be like 11100. So if we binderize all of this data. So now you see this is a real world problem. So this is a real world problem which we have somehow taken into the binary world, and then what we did is we can now apply all the things that we have learned so far. So now I showed you that this binary, even if we just work with binary things, if we work like with AND gate, I showed you how to model AND gate, how to model OR gate by using these perceptrons. So now you can similarly model, you can similarly take this binary data, and now you can sort of create a maybe a multi-layer perceptron, of which we'll shortly see how. But I just wanted to pin this down that you can also use this binary data. So it will have a lot of examples in the real world. You will see that you can have this binary data, so that and they reasonably perform good. Okay, so this is one of the example. Now we'll see that what are limitations. The problem is we saw a lot of things in binary only. So now we want to see the limitation of these perceptrons. Okay, we saw two things. We saw Michaelo-Pitts neuron, and then we saw a perceptron. So I wanted to show you the limitations also. So what is the limitations? Just keep this example at the back of your head. This example, I just wanted to touch on this example because I'll use this as a running example everywhere. Wherever I have to use some example, I'll just refer to this example. So now first we'll see limitation of Michaelo-Pitts neurons, and we'll also see the limitation of perceptron. Okay, so the limitation that we already have just mentioned, now we'll discuss it thoroughly, was that it cannot model XOR gate. It cannot model XOR. So basically, to just generalize this, it is not capable of modeling what are non-linear, which is when the data is non-linear. So I said that if data is linear, if you have linearly separable data, then you can take this perceptron or molecular pits neurons, then it can perfectly come up with a decision boundary which will divide into two classes, positive half space and negative half space. The limitation comes with this nonlinearity if the data is nonlinear. Okay, let's see what is the problem. We'll see with XOR gate. Okay, so if we see XOR, so XOR has say two inputs, X1, X2, and then you have XOR. This is the output. So this is 0, 0, 0, 1, 1, 0, and 1, 1. So in this case, you have this. Okay, so this is the truth table. Now let's suppose if you see, you know that how perceptron is defined. So perceptron is defined W naught plus W1 X1 plus W2 X2 is greater than or equal to 0, then you have 1. Okay, else otherwise this is 0. So this is the definition of perceptron. Now let's suppose, so if we put these values over here. If you put these values W1, X1, W2, X2, so this over here. So this is our X1 and this is our X2. So now if we put these values in this case, so you will get, so for each of this, we'll get some condition. Okay. Let's suppose for this 0, 0. So 0, 0 gives us 0. So how can we do this? This is W0 plus W1 multiplied by 0 plus W2 multiplied by 0. Okay. If you see this, so this should be less than 0 because we want this to be off. So this should be less than 0. So now what you can see is you can see W0 should be less than 0. So this is the first condition that we got. From this case we got 0, 0, that is 0. So we just substitute the values in here and then you got this condition. Okay, then second thing. So we have this 0, 1. 0, 1 gives 1. This is how XOR is. Now you know you just have to substitute the values of W0, W1 and W0, X1 and X2. Okay, and then we'll see this. So let's suppose this W0 plus W1, X1 is, let's suppose in this case 0 and plus W2, 1. Okay, now we want this to be greater or equal to 0. So this should be greater than or equal to 0. Now what you can see over here is W2 is greater than or equal to minus W0. Okay, this is the second case that we got. The first case is W0 is less than 0. Second case, W0 is greater than 0. Similarly, for other cases, what you will get is you will get W1 is greater than or equal to W0. Okay, and then the fourth case you will get is W1 plus W2 is less than minus of W0. So this is the four cases that you will get. Okay, let me just enclose them in the box. I think this should be clear to everyone. No problem in this. So now you have this four cases. Now if you see this, so there is a contradiction in these inequalities. Okay, if you see from this 2 and 3 you will get W1 plus W0 is, so basically if you just combine them, so what you will get is you will get W1 plus W2 is greater than minus W2 naught, and then you will from condition 4 you will see that W1 plus W2 is less than W0. So this is a contradiction in here. So this is contradiction. So when you see this, so it is impossible to now solve it. Okay, so because the thing is you won't have 2c is less than this is not equal, this is not less than c, or c is not, while c is greater than 0. So you can clearly see that there is this contradiction. So when you solve these four inequalities, so this is inequality number 1, number 2, number 3 and number 4. Okay, if you try to solve these inequalities, you will get to this contradiction. And now you clearly saw that we cannot have any values for W0, W1 and W2 where we can separate out these, where we can somehow classify these, that this is a positive class or this is a negative class, this is a positive half space or a negative half space. Everybody with me so far? So if you see this, what is now appearing on the screen? So I have given this labels A, B, C and D over here. So this is that labels which I have given. So this is A, B and C and D. And now what I will do is I'll suppose write the equation, say W naught, or maybe minus, will give some constant value to W naught, maybe minus and plus, say W1 multiplied by X, okay, plus W2 multiplied by Y, and we'll have sliders for these. W2 multiplied by Y. Okay, something of this sort. Okay, so if you see this is a line. So now if I move it around, so you'll clearly see that nothing will happen. So there is no way that I can have this line in such a way so that, so this point, if you see these 2 points, so 0, 1 and 1. So I should somehow separate them. As I should have one class of these points and I should have this 1, 1 class. This is the other class. So basically this is class 1 point over here. So point this and this point. If you see these corner points, and if you see this point and this one, this is class second. So if I can color that with a different color, so this and this over here. So this is two classes, but you can clearly see that there is no way if I can take a line and I can separate them. I can classify them by using a linear surface, by using this line. Okay. I hope that you people agree on this. Whatever values you give to this W0, W1 and W2, there is no way that a line can separate these two classes out. Okay, there is no way up. There is no way like that. Okay, there should be a non-linear surface of this sort. Okay, maybe this is the surface, and this surface is somewhat non-linear. Okay, so internal to this surface is class 1, exterior to this surface is class 2. Okay, this is the surface which could separate it. But now, given that we have this line, there is no way that we can adjust, we can give any values. You can try it at your home by giving any values to this. So you won't be able to get these two classes separated by using a linear surface. I hope this is clear to everyone. So what they show you this example. The motto of showing you this example was that there are some things which cannot be modeled by using this perceptron, by using a single perceptron. Then what should we do? So the resort is we should go to multi-layer perceptron. Okay, we should go to multi-layer MLPs. Okay, and we'll shortly come to that, but we'll do some treatment of these Boolean functions. Okay, let's suppose that we have this, say we had these functions x1 and x2 were the input, and then you know that 0 0 0 1 1 0 and 0 0 were the possibilities of input that we can give to this, and based on this how many functions are possible. So we can have function f1 which will have all zeros, so it will be off everywhere. We can have function f2 which will be 0 1 0 0, something of this sort. So can you tell me how many such functions are possible? I'll give you a second to think. The question goes like this: if you have n inputs, so how many functions are possible? Yes, please. So now the question was, with n inputs, how many such functions are possible? So if we have n input, that means we have 2 to the power n possible combinations of these inputs. Now each of this again can take 0 or corresponding to these combinations. Let's suppose corresponding to this, it can take either 1 or 0. Corresponding, it can take 1 or 0. Now if you have this 2 to the power n combinations possible, then total functions will be 2 to the power 2 to the power n. These many possible combinations. So now in this particular case, you will have 16 functions. 2 to the power 4, 2 to the power 2 to the power 2. That is 2 to the power 4. That is 16 functions. So you know, out of these 16 functions, 2 are linearly non-separable. So 2 are non-linear. 2 functions are non-linear. So one function is XOR, that is non-linear. I think second function is XNOR, if I'm correct. So these two functions in these 16 functions are non-linear functions. Okay, they cannot be modeled by using our perceptrons or Macaulay-Pitts neurons. I hope this is clear. So now the question is, how many such functions will we know? If I give you, let's suppose, n inputs, and if I say, okay, the possible combination is 2 to the power 2 to the power, and total number of functions is this much, or how many functions are there which will be non-linear? Okay, so this question is unsolved. This is an unsolved question. Nobody knows. Okay, there's a mathematical problem. You can try it on your own to find how many functions will be non-linear, but so far I haven't found any solution for this. Okay, now you saw that there will be a lot of functions which will be linearly non-separable. So we'll have some functions which will be linearly separable. Then we'll have other functions which will be linearly non-separable, and non-separable functions will be the functions which cannot be modeled by using this perceptrons or Macaulay-Pitts neurons. Okay, now we'll have to generalize somehow. We'll have to do, okay, what to do with this. Now what we'll do is we'll come up with this multi-layer perceptrons. We'll see MLPs. Okay, now we'll shift to our gears to multi-layer perceptrons. Multi-layer perceptrons. The constant question that we have to solve is, okay, now somehow we'll have to come up with these neurons. We'll have to combine these neurons somehow so that we can model any given Boolean function. If we are given a Boolean function, so we should be able to model that. And as I showed you, why only Boolean functions? So I showed you one example that any problem can be made. We can binaries that, and I showed you example of that. If a product will be purchased by a customer, okay, that's why we're interested in Boolean, and maybe slowly we'll move to the real world functions as well. Okay, now that is the reason we are going to this multi-layer perceptrons. So why is it failing? So you saw the reason of failure. So we had these contradictions. The contradiction that you saw is that we had these inequalities, and so there was this contradiction in the inequalities. Now the question is how to solve that. Okay, so there should be some way of solving it. So how to solve that now? So in order to solve this, I'll give you some idea, and then we'll have a discussion on that, and then we'll come to the solution on our own. Okay. The solution is like this. So you had just one perceptron. You had this, and then you have input x1 and x2, and then there was some output. Okay, maybe because of this you are getting some issue. So because you are using only one neuron, so you're overloading that. So every condition was sort of, you're only giving this neuron that condition, or you are giving these inputs to this, and it was the four inequalities that were generated. They were generated because of this. Now, what I want you to think is, can we somehow make multiple of these neurons, which can handle these different inequalities on their own, and we just want to separate it out. So initially, the concept goes like this. I'm telling you that this neuron is somehow overloaded. So why is it overloaded? Because all of the inequations that you saw, so you saw four inequations in case of XOR, so they were produced by this, because this was given x1 x2 four combinations, and it had to give some output. So what I'm telling you now is, so now can we do this thing? So you had this input output pair, you have possible combinations. Now for each of the inequality, just have one neuron, have the one neuron, and then combine them somehow. Okay, how many of you got this idea? You can clearly see that the problem arises because of this, because we were somehow overloading this neuron. We were overloading this, and it was generating four inequalities, and we couldn't solve that four inequalities. Now, what I'm telling you is the solution lies that you should somehow handle each of the combination. So the combination that you have, or the permutation in particular you have, so you should handle that by a single neuron. Okay, and then somehow combine these neurons. So that will give rise to this multi-layer perceptron. Okay, in this case, so we have four combinations. So if we have two inputs. So if you have two inputs, so you have four possible combinations. Now what I'm telling you is, I'm suggesting that we make four neurons. Okay, so this is the four neuron that we have. So once we have these four neurons, so what we can do now, so we can make these four neurons handle each of the possible combination. Whatever we had, so let's suppose 1 0 0 1 0 0 or 1 1. So each of this will handle a different sort of inequality, and this will not lead to the contradiction. So this will somehow save us from that contradiction that we had initially when we had just a single neuron which was generating all the equations. So what can we do is simply, so I'll just modify this problem so I have to show you this. So we'll now consider plus 1 as 1, and 0 will be replaced as minus 1. So we'll have plus 1 and minus 1, so that we make this problem much simpler. So this is 1 and this is 0, just a simple replacement. So wherever you see minus 1, that basically means 0. Okay, now what we'll have this x1 and x2. So I'll write x1 and x2. So this will be our input. Okay, and then we'll have an output. So here we'll have an output. So this over here will be output, and this is our input. So I'll write input over here. This thing is called a hidden layer. Now we'll have to somehow make this such that we'll model XOR, let's suppose. So we'll model XOR, because that is the problem. If we solve that problem, and then we can generalize it. And I told you core idea. The core idea is that, so once you have each of this neuron handling a separate case, and then we'll see if the contradiction can be solved somehow. If that is solved, then we can just generalize it. So now what I can do is, I'll write maybe with this red. Red will mean, how can I write it? I'll write it here. Red will mean, say, minus 1, and we'll have, say, maybe this blue or purple, whatever this color is. So purple will be plus 1. So I'll make these connections now. So starting with this, so this will be red, and this will be given red. Okay, similarly, what I can do is one red and one purple. This is basically 0 1. This is 1 and 0. This is 1 1. How many of you understood this? So over here, if you see, this is minus 1, minus 1. So this is minus 1, plus 1. Okay, that is basically 0 1. So this is 0 0. So this is 0 1. This is 1 0, then 0 0. So this is what we have demarked over here. So these are the connections that I made. And then what I can do is, I can now combine all of these. So we have function which will combine all of these. So we'll combine. So now each of this output, I can write it. Let's suppose this output can be O1, O2, O3, and O4. And this is the final output. Let's suppose O final. this will be final output. And here we'll now also assign weights. So we'll say this is W1, W2, W3, and W4. Okay, now I sort of made a multi-layer perceptron. So now I have multiple perceptrons here. If you see this perceptron, this, and this, we have 4 perceptrons in the layer. And now I can say bias also. So let's suppose bias is equal to -2. I'm constructing this. So what I now claim is that this will model XOR without problems. Okay, now I'll tell you why. Why will it model XOR? So let's suppose this. When will this neuron be activated? Okay, so if bias is -2, so when this is -1 and this is -1. Okay, let's suppose then only this neuron will get activated. So you will only have one neuron activated. So once you have this, because this bias is -2. So basically bias means if this is greater or equal to -2, then you activate it. So for -1, -1. So you'll get this. Let's suppose you will add this up with this. So you'll get this activated. Or we can also say the reverse. We can add the bias have +2. Maybe have bias +2 so that it is greater or equal to 0. So this is -1 plus this is also -1 because input, if you see. So let's suppose input give input -1, -1. I think bias should be -2. I was right. So -1, -1. Once you have this, so now these connections are -1, -1. So -1 minus is +1, +1. That means 2. 2 minus 2 is 0. So this will be activated. This will be only activated if the input is -1 and -1. So this neuron will get activated. So I can write this over here. So if you have -1, -1, this will be activated. So all the other won't be activated. How? Let's suppose take this example. So this will be -1, say -1. This is 1. -1 plus 1. This is 1. So this will be 0, and it won't make this bias 0. So here we had 2, then -2, it was 0, and it was surpassing the bias. It was greater or equal to this. But this case, it will be again -1. So you have 1, -2, that will be -1. It won't be 0. Similarly, in this case, same story. Same story in this case also. Okay. When you have this input -1, -1. Okay. Now if you have this input, let's say -1 and +1. Okay, now you see this is -1 and this is +1. So this will get activated. How many of you are understanding this? Can I assume that you are understanding this? So what I'm saying in here is, to clarify again, so I'm saying bias is -2. So when you, let's suppose surpass the bias, so when you pass this threshold, then only you will get activated. So when you give this -1, -1 input, so this will make it 2. And the bias is also -2. So 2 minus 2 is 0, so this will get activated. Okay. And similarly, when you have this, so because we have this, that this will get activated if it is greater or equal to 0. Okay, now it will be 0 because bias is -2. This will make it -1 multiplied by -1 is 1. -1 multiplied by -1 is again 1. So initially, and then what will happen is, so this will be +2, -2 is 0, so this is activated. All others won't be able to get this bias because you have this -2 is the bias. So this will only produce +2, so that you can surpass this bias. Otherwise, for all other combinations, it won't produce. So all of these, if you see this -1, -1, so this will be 1. Then you have +1 multiplied by 1. This is again 1. So 1 minus 1 is 0. So it is not surpassing this. So you should at least have +2 in order to surpass this. So +2 -2 is greater or equal to 0. Similarly for all others. So you have the same case for here. So in this case you have -2. So -2 -2 is -4. So in this possible combination -1, only this neuron will get activated. Okay, because this is the only neuron which will be able to pass the threshold. Basically, it is giving +2. So +2 -2 is equal to 0. So it is greater than or equal to 0. So we'll fire this neuron. So is it clear for everyone? Any questions on this? So if you understood this, okay, just summarizing this. So you had input. So we made sure that the premise that I said is that each neuron should somehow handle one possible combination. So if we make one neuron handle one possible combination, then we can say that we will not have now this contradiction in those inequalities. So let's check that also now. Okay, now let's check that. So if just have this diagram in your mind. So now you had this x1, x2. So this could have been -1, -1, -1, +1, +1, -1, and +1, +1. Now XOR would have it 0. This is 0, 1, 1, and 0. Okay, then you have this O1, O2, O3, O4. O1, O2, O3, O4. The output that you get at this position, O1, O2, because now you'll have to multiply all these things. Okay, then only you'll have to make sure this is there. So for this O1, so if you see this, so this is 1, 0, 0, 0 for the first case. Okay, O1 will be activated only in this case. And second thing is, let me just color it like this. and this thing will get activated in the second case, and this thing will get activated in the third case, and this will be activated in the fourth case. Okay, this output will be only activated once we reach the hair. Okay, if you now take this, so summation of all of these, so now you sum this up, so this over here, so output final, so I can write it O final. So what is O final? O final is summation of all of these, summation of W1 O1 plus this is O2 W2, similar like this I can write summation of OI WI. Now if you see this, so this will be W1, this will be W2, and this will be W3, and this will be W4. Okay, if you just sum these things up, so this will be W1, W2, W3, and W4. Now let's suppose in the first case, you'll have W1 should be less than W0. Why? Because you don't have to fire in this case. Okay, in this case, you don't have to fire. In the second case, you have to fire. That means W2 should be greater than or equal to W0. And in the third case, W3 should be greater than or equal to W0. And W4 should be less than W0. Because here in these two cases, you don't have to fire. Not fire the neuron. So in the two cases, you have to fire. Now you see these four equations, you see these four inequalities. There is no contradiction. You can solve it. You can find values for W0 such that all of these things are satisfied. So there is no contradiction. There is no contradiction. So how many of you can see this, that there is no contradiction in this? It is clearly visible over here. So if you see, because I made sure that each of this combination is handled by one neuron and only one of that gets activated. So if you now see this, so W1 in the first case, this W1, because we have to make sure that this does not get activated in this case. Okay, this is the activation XOR. So we'll say that this should be less than W0. It should not cross the threshold. Okay, so W0 should be set such that it is W1 is less than W0. In the second case, W2 and W3, we have to set these values such that they should surpass this W0. They should cross this threshold. Okay, or at least be equal. And in the last case, W4, it should be less than W0. And now if you see this inequality, what I said is there is no contradiction. You can set values for W0, W1, W2 in such a way and W2, W3 in such a way so that there is no problem with this. So this over here, this is modeling your XOR. So this is perfectly modeling your XOR. How many of you agree on this point that this is modeling XOR? Okay, now we can generalize this. Okay, we can generalize. So we can generalize this architecture to all Boolean functions, all Booleans. Because you know the core principle. The core principle is that you have to make sure that one neuron handles one combination so that you do not fall into the trap that we can have some inconsistencies or we have some contradictions when we form these inequalities. Okay. So now if you have n inputs, that means corresponding to n inputs, you will have 2 to the power n possible combinations. So that means we will require 2 to the power n neurons. 2 to the power n neurons to model that. And then we can map anything. So basically this is showing you the expressive power of these multi-layer perceptrons. So you can just have one hidden layer. So one hidden layer with 2 to the power n neurons. Okay, you can map any Boolean function with this. Now the interesting question is there a way? Can we optimize these neurons? Can I use less than 2 to the power n neurons somehow? And I don't have one layer. Can I have multiple layers? Okay, that's the question we'll answer maybe in universal approximation theorem. But this question is the answer to this question is this. Yes, there is a possibility that you can reduce the number of neurons in that. Okay, so now the terminology that I said is we had input layer. Input layer is, it's not basically a layer, it is where you take input from. Okay, input, and then we have these hidden layers. So hidden layer is where the computation is happening, and then output is where you take the output. So in this case, you saw this. So here this was input, this was your hidden layer, and we can have multiple of hidden layers. And then this is our output where we'll gather these output together. And now this is one more motivation of deep learning. So I said one motivation was from that experiment by Hubel and Wiesel that did an experiment where they saw the hierarchical data extraction. This, and the second was this, because we couldn't model these non-linear data. We were not able to model that by Mikolopitch neurons or multi-layer perceptron or single-layer perceptrons. Not even layer perceptron, single perceptron. So as a solution to that, we now combine these neurons in at least a layer. So we had input, then a layer, and then an output. And we showed by construction. This is called as proof by construction. This is a technique of proof. It's called as proof by construction. We have directly given a proof of construction. So if anybody asks you, okay, what is the proof that this also works? So you just give the construction steps. The step 1 is take input, step 2 is have these many number of neurons, and step 3 is add weights and biases like this, and step 4 is compute this. Okay, so this is the proof by construction of the thing that we can model any Boolean function of inputs with one hidden layer of 2 to the power n neurons. I hope this is clear so far. Is it? This is what we solved. We saw this problem and we solved it for binary. Now, in the real world scenario, the whole data is not binary. So we had two problems initially. Initially, we solved it for binary and linear because we know that. Okay, let's suppose if we could solve it for binary and non-linear. Now we had solution for that also. Okay, now we have to somehow make it generalized. We have to generalize this to real numbers. Okay. And before going to the real numbers, and I'll also have the same running example over here. So you see this. This is the example. Suppose we want to have this data because this data won't be usually binary. So you'll have time spent in minutes. You'll have extra number of products will be a discrete number. Average will be some floating point number, and then this will be because this problem is a classification. It will be having a value y is equal to 1 or 0. That is, the person will purchase the product or person will not purchase the product. Okay, then you have this real world problem. Now, if you see this, if you see this thresholding logic or things that we saw the perceptron, because this perceptron basically what it does is it was using this thresholding logic. It was saying that if let's suppose you have summation, it is this wixi is greater than equal to, let's say, some theta some threshold, so give it 1, otherwise give it 0. So this was what perceptron said. This is perceptron. Okay, so the activation function basically. So what I'll now call it formula as activation function or the decision function. Decision function. Decision function was quite absurd. Why? Let's suppose I'll take this example. Say you are doing the same thing. You are doing this product purchase. If I have to recommend this product, and if the person will purchase the product, or similarly movie recommendation. Okay, for movie recommendation, will the person watch this movie, or something of that sort. So let's suppose the threshold is 0.5. Say threshold is 0.5. So if this summation wixi, okay, if this is let's suppose greater than 0.5, then you can say okay, person will purchase the product or person will watch this movie. So if let's suppose if this came out to be 0.49, say you will straight away say that 0. The person, we should not recommend the movie or we should not recommend this product to the person. Okay, but you see that there is very less gap is there, 0.5 and 0.49. So the decision varies a lot. So you see, this somehow looks very absurd. For how many of you this looks absurd? At least when I saw this first, it looked absurd to me. Okay, you are changing your decision. You are having this. There is a clear cut. If it goes above this threshold, then only you make it a file. Then only you purchase it. Okay, somehow we'll have to find a solution to this. Okay, so we should now this decision function or the activation function had some problem. So if you see this is a step function in our case. So this was like this. So if I make a graph, so this graph would seem like something of this sort. So let's suppose 0.5 is the threshold. So you'll have say 0.5, this will be activated or this will not be activated. So say till the value is not a particular value, so you'll have the 0. So say at this point you have this 0.5 and then you suddenly jump. Okay, this is how the function will look like. Okay, so this is 1 and this is 0. Okay, and this point is the activation point. So what we found is that this logic is quite harsh. Why is it quite harsh and absurd? Because you see that 0.5, if the whole summation, if this aggregation function, the value was, let's say threshold was 0.5, then you would recommend the movie, or you would say that okay, the person will purchase the product. But if it was slightly less, that is 0.49, you can see that oh, it is directly saying 0. But in the real world, this is not how things work. Okay, in the real world. So basically what we want is we don't want this step. We want something which is smooth. So by smooth, I want a function of this sort. I want a function like this. So let's suppose it should be 0, 0 and then it should slowly go. Okay, and then it should taper off. Something of this sort. Okay, I want this smooth function. Okay, so how many of you agree on this point? I don't want sudden jump. So what I want is basically I want a smooth curve of this sort. This is 0 to 1. So it will start, let's suppose, from 0, 0 and it will slowly go, and after a point then it tapers off. Let's suppose, so after let's suppose 0.8, you can give the value 1 always, something of that sort. So that this curve is somewhat smooth curve. Okay, the curve that you see over here. So you see this is somewhat a smooth curve. Okay, in this, what is the behavior of the curve? So if you start with 0 and you slowly, you can see that the value is increasing. You can clearly see the value is increasing over here. And after a certain point, the function tapers off. You can see that this is called tapering off. This behavior is called tapering off. Okay, so this is the behavior I want. How many of you agree with this behavior? That we want this sort of behavior. This is the behavior that we want. We don't want a sudden jump. Okay, so a lot of research has been done on these functions. A lot of people studied these functions, activation functions, and they wanted some behavior like this. And that's why you have been hearing terms like ReLU, sigmoid, this, that, and all of these functions basically have this behavior, and they want to remove this behavior. They want to remove the sudden jump behavior. So what they basically want is they want this smooth behavior. So if we now have this, so you have the aggregation function. If you keep the aggregation function same, so you have same aggregation function, same aggregation, and now you come up with a function. Okay, this function, let's call this as this s-shaped function. There are a lot of mathematical functions which will form this s shape. So one of them is called as sigmoid. Okay, so sigmoid is a family of functions. There are a lot of functions which are called as sigmoid functions because they form this s-shaped, they have this s-shaped behavior. So now you have same aggregation function, and you take one of the sigmoid functions and you call this as sigmoid neuron. So what is a sigmoid neuron then? So, and you know the reason also. So we had this very harsh function which had the sudden jump, which was taking a threshold logic. If you have threshold at this certain point, and then only you fire, otherwise you don't fire it. Then we wanted a smooth behavior of this sort. Okay, and as I said, there are a lot of functions like this. So sigmoid functions is a family of functions which show behavior of this sort. Okay, we'll see maybe logistic function, we'll see tanh function. All of these are sigmoid functions. So let's say how is this logistic function? So we'll take one function which is called logistic function. So if you now see this logistic function, so how is it? It is y is equal to 1 divided by 1 plus e to the power minus, let's suppose call it x. This is the logistic function. So this is again a sigmoid function because sigmoid is a family of functions. So this is how it behaves. Or maybe I can write it something of z or something because x will be used a lot. X naught, y naught, something of that sort. Okay. Say you have this y, so you write it like this. So you have w transpose x dot product, and you will write sigma like this. Okay, so what is the value of this? So this will be equal to, this is 1 divided by 1 plus e to the power minus w transpose x. Okay, and this function will have this behavior. It will have this behavior. You can change this w naught, w1, w2, and you can expand it, and it will contain this behavior. And the beautiful thing about this is this gives values between 0 and 1. So this sigmoid function gives values between 0 and 1. Let me show you the sigmoid function again on Desmos calculator. Give me a second. I'll show you on the Desmos. So if you see this, so here I have given values w0, w1, and w2. So if let's suppose this is our perceptron. Okay, so this is a linear perceptron. So you can see this. Okay, so you can see this perceptron. I can write a function which will just take values over here. So what actually I want to show you is this function. So this is the sigmoid function. If you see it over here, you see this S-shaped curve. So how many of you can see this S-shaped thing? So I believe everyone can see this S-shaped. So now what is in this S-shaped? If you see over here, it starts with 0 and goes to 1. Okay, I can zoom it a bit to show it clearly. So this curve over here, so this is a logistic function. Okay, so in this particular case, this is logistic function, and the function is over here. So you see this, the function is here. Okay, and this over here is a logistic function. This is logistic function. Basically, as I said, sigmoid is a family of functions. So you can now see that it starts with 0 and slowly goes up, and if you see exactly at this value 0, you can see this. If you go to, and you will find 0.5 in the middle. Okay, somewhere around here. I can't read this because this is so small. And then you will see that if it goes towards larger values, and then after a while it goes continuously to 1. Okay, and this is the behavior actually we want. So let's say if you see this function now, if you see this function, that is 1 divided by 1 plus e to the power some minus z. Suppose the z value is, let's suppose it is going to minus infinity. If you say, let's suppose it goes to minus infinity. So we'll take the extreme values. So what will happen is 1 divided by 1 plus e to the power infinity. Okay, and this will be 1 divided by infinity, that is it will go towards 0. So if it goes to minus infinity, and you will have the value goes towards 0. Okay, and now what will happen is if it goes towards plus infinity, okay, you see the value will go towards 1. So if you increase value, basically it starts with 0. I wanted to show you this. It starts with 0, and it goes till 1, and it keeps the value between 0 to 1 given the values. And if you have, let's suppose, value say in the middle, and it will be some 0.5. And one more thing that you know, probabilities also have these values. So probabilities are the values which are between 0 to 1. So this has one more case in that. So one thing is, it's a smooth function. So what I mean by smooth, it is a continuous and differentiable function. Okay, and why do we care about differentiability? Because you know that we'll use back propagation and we'll have to differentiate these functions. And this function is smooth, that it is continuous and differentiable. And because we'll be using a lot of calculus for back propagation, we'll have to flow the gradient and all of these things. And these are the functions that we'll require, because you know that we'll apply on these neurons, the neurons that I made just now. So these things will have activation functions now. Okay, so activation functions will be written somewhere like this. So you have activation functions. So now once you compute the gradients, so your function should be a smooth function. It should be a continuous and a differentiable function. Okay, this sigmoid function over here is a smooth and differentiable function. And the second thing, it mimics the real world also. It mimics real world scenarios. Okay, so why does mimic real world scenario? Because I showed you the example. It's not that harsh function, which we had, that step function was quite harsh. So at 0.5, you are suddenly saying that, okay, if the value is greater than 0.5, then we'll recommend this movie or we'll recommend this product to a person. If it is less than 0.5, that is even 0.4999, you won't recommend. But now what is this giving? This is giving you the values which somehow mimic the reality, because it does not take harsh decisions. And it also is in terms of probability. It can be viewed as probability. Why? Let's suppose if the value came out to be 0.67, so this is the product recommendation is 0.67. It will give you like this. It will say that with this much probability or with this much success rate, you can recommend this product. So you can sort of understand these in terms of probabilities. Okay, I hope these three things are enough reasons to come up with better activation function. So this activation function is a great research area. So people still research on this research area. People almost like every year you will see a lot of functions, activation functions coming up. You will see that swigglue is a function which Meta came up with, and then you have a lot of these functions. And I think there has been a lot of things that have been done here, and now people are researching a bit less on this area, because now we have a lot of these functions where somehow people believe that these results are at par, the results that we wanted to get by using these activation. But still, it's a very good research area. I don't see many types of aggregation functions. So the aggregation function you usually will see is this. So you will see this aggregation function directly. When you say dot forward, so this is what it does. So now you see this two things are here. So you have this forward pass. So what is this forward? We'll still see it in detail, but I just wanted to show you this. So when you perform this W transpose X, so you do this computation, and then you apply an activation function of this. So this is called as a forward pass in neural networks. Okay, so you have a neural network. So in that, once you perform this computation, now you know about neurons. So you have this, I can make a diagram, rough diagram. Okay, so now this is, let's suppose this is our input. So x1, x2, something of this sort, or maybe I can create one more layer. And this is x1, x2, x3, and x4, x5, something of this sort, x4 input. And once you compute this, so you'll have weights and biases. You'll have weights and biases associated with this, and each neuron will have its activation function. So if you perform this to get an output, so this is what is called as forward pass. So you do W1 x1 plus W2 x2 plus W2 x, then apply this activation function for all these neurons till you get here. This whole thing is called as forward pass. And then we'll see that there is a backward pass. So in backward pass we have, so in forward pass you compute the stuff. You compute to get the result, to get towards the result. So in backward pass you learn. So in the backward pass, there is this learning happening. Okay, so now you saw an architecture. So I wanted to show you why is this learning happening now. So you have this forward pass, you have this computation, and then you compare. Okay, it is giving me this results. So is it the right result? Oh, these are not right results. Okay, now let's do backward pass. That means I have to adjust these weights and biases. So adjustment of these weights and biases is done in backward pass by using an algorithm known as back propagation. So back propagation is done by gradient descent. So gradient. So we'll have to now do a detailed treatment of what gradient descent is and how backpropagation works. And before that, we'll first try to code these neurons and then do the forward pass. So two important things. So one important thing is that you have this forward pass. So once you create a neural network, and this is called as the architecture of neural network. So what is architecture? Architecture is basically how are you combining these neurons now. So now you see a lot of research areas are there. I said one research area is activation function. Why do you come up with activation functions? Okay. So I said I saw I almost have never seen some research on this aggregation functions, because people somehow believe okay W1 X1 and summation of this is good enough. Okay. And you see these activation functions. Now how do you combine these? What is the architecture you will do? Okay. You have these neurons now. How will you combine these neurons? What blocks you will keep? Let's suppose I'll create this block. I'll have these many layers. Okay, these many layers with this input size and with this output size. This all is called as architecture. Okay, so we saw some terms. So we saw architecture, we saw forward pass, and we saw backward pass. So what is architecture? Basically, how are you now doing the arrangement? Now you know about neurons, and now you have to arrange them in a certain ways. And then these architectures can get very complex. Okay, and then you'll have to reason. Okay, why am I creating this architecture? What I need by this? Okay, so you have this architecture, and then you have this forward. What is this forward pass? Every architecture will have this. Now you have to compute once you have this weights bias input. So what will you do is you will take this input and you will perform these computation. Basically, W transpose X, and then you will apply activation functions at every neuron. You will do aggregation and then apply activation, aggregation, activation, aggregation, activation at every neuron till you go to the end. But once you go to the end, so what will you do, and you will get a result there. So and then you will result, and the whole of this process is called forward pass. Till you go from the initial input to the final output that the network is giving. So this is called forward pass. Then you compare it with the ground reality, and you compare it with the things that you want. So once you compare that, then you have the possibility of learning. You have to adjust these weights and biases, and then you have to flow the information backwards. Okay, so by using the back propagation and gradient descent, and you do the backward path. This is where learning happens. Okay, so far you have understood backward pass. You have understood forward pass, and theoretically also you know what backward pass is, because it's all by using gradients and then flowing it. And now the task is we'll have to put all of these things together to train it. Okay, so in architecture, the first thing that we'll have to create is a neuron. So we'll write a Python code which will create neuron, and it should be able to create these operations. Which operations? It should be able to add, subtract, multiply, exponentiation, and all of these things should be done within this neuron. So this is a data structure, or we'll make a class of this, and after that we'll make sure that it does the forward pass. Okay, and then we'll see it does the, and we'll have to write back propagation algorithm so that it does the backward pass. And then in the architecture, we'll combine these neurons together. Okay, and we can create a layer, and we can, let's suppose, create a CNN layer, and all of these things come in the architecture. Okay, now I'll wrap this lecture up today. So maybe we'll take it in the next session from here, from coding to the neuron till go to forward, and we'll go to forward pass, and then we'll code the propagation algorithm, and then we'll be done with the at least basics of deep learning, and then we can move on with different architectures. Am I clear on this? Any questions?